My research primarily involves mathematical modeling and simulations of fluid flow systems. The thing that we are working on is fluid mechanics associated with reacting flow system, which involve chemical reactions, like in engines of cars, engines of airplanes, for space shuttles, anything that involve chemical reactions and involve fluid mechanics. What we do primarily is on mathematical modeling and computational simulations of those. We perform all of our experiments on the computers. We use the supercomputers like the one we have at Pittsburgh Supercomputing Center, and we use the state-of-the-art computational procedures to simulate fluid flow systems. We always want to improve the efficiency. We want to come up with a more advanced design. Maybe you're talking about engines of cars, but how about engines of airplanes, engines of space shuttles? You know, X series of planes that are developing now. If you want to fly at a Mach number of 20, you know, like 20 times the speed of sound, you have to have an engine design to be able to do it. You want to have more fuel efficient engines. You want to have an engine that produces less NOx. You want to have less pollutant, more efficient, you get better gas mileage out of it. You want to have more powerful. So that you want to come up with a new engine. First you have to come up with a mathematical model to describe the temperature, to describe the velocity, describe the density of the fluid, whatever else that you need to know. You use a lot of your knowledge of fluid mechanics, chemistry, physics, some of the fundamental science, use that knowledge to come up with mathematical models. Now, development of the models is one thing. You can come up with a very sophisticated equation and they are very powerful. Then the issue becomes how do you solve them? What you need to do to come up with a sophisticated computational methodology and a sophisticated mathematical model, and also a sophisticated way of coupling these two together, that your computational method can actually solve this equation and give you what the physics of the flow is. I have developed a new methodology, and it has been proven to be the way of future in any kind of a simulations involving turbulent combustion. Engines, by design, they involve turbulent flow. You want the flow inside of an engine to be highly turbulent, because if it is highly turbulent, it mixes the fuel and the oxidizer much more efficiently. One thing we know in classical physics, one of the problems have not been solved is turbulent fluid mechanics. So we have to come up with models to solve this. Our methodology when it comes in turbulent combustion has proven the best. The center of energy at PET, if you really look at the center in comparison with all the other centers that have been created across the country, is one of the most unique because of diversity. And the people who are involved in it are the best that there are in that particular field, that are involved in phenomena that goes from very, very large to very, very small scale. Our methodology simulates flows from orders of kilometers all the way to the order of microns or even smaller. So that's the uniqueness of our center is. Our success is by the visibility of our students. To see them develop, they're coming in as 21, 22-year-old kids, coming in, and by the time they leave in the mid-20s or late 20s, they go out as a very confident scientist. One of the things seriously we're very proud of is the fact that our PhD students have had the top-notch jobs in the countries. Almost all of them have won the major national awards, like the career awards, the young investigator awards of some sort. That they are going out with a very large visibility. People know who they are. They publish in the first-ranked journal, and they can go anywhere they want to go. Within the past 20 years or so, we have had funding from Department of Defense, including the Air Force and the U.S. Navy, and we have been heavily involved with NASA. Most of our work has been continuously being funded by NASA through major programs. With NASA Langley in particular, that they have been funding some of our mathematical and computational methodologies. I really hope to see at least happen is that my methodology to be used by a larger number of companies. One thing I really like to see, without any compensation of any kind, if they want to invest the time to send their engineers to learn about our scheme and implement them into their code.